Hello and welcome to Mathematics Illuminated, where I shed light on any and all math topics from simple to advanced in a way that is easy to understand and interesting to learn. Please subscribe to my channel as I continue to post more videos, and comment below on videos you'd like to see in the future. Today I will be going over the product logarithm, a function with interesting use in mathematics. The product logarithm is symbolized as Wn of x, where n is any integer and x is any number both real and complex. Here the n just means the branch of the product logarithm you are looking at. Other names for the product logarithm include the Lambert W function and the omega function. The product logarithm is defined as the function where Wn of x e to the Wn of x is equal to x. It is also common to remove the n's for sake of simplicity, and only apply them later when you are finding the product logarithm at a particular value. Here, w of x would just represent a general solution to this equation. The product logarithm shows up when we are asked to solve an equation like this in terms of x. Solving it gives that x is equal to the product logarithm of a. Then, once we are solving the product logarithm of a certain number, we can include the n again to specify which branch we are solving for. Allow me to demonstrate what this means further. Here I have the graph of y equals x e to the x. We know that solving for this equation gives us the general product logarithm of y. Here we see that as y approaches infinity, the product logarithm also approaches infinity, and as the product logarithm approaches negative infinity, y approaches 0. Now what I'll do is I'll switch around the x and y variables, so that now we are graphing the equation of y equals the product logarithm of x. Notice that the graph does not go past the x direction at a certain value. This point here is where the x can be the smallest and also have a corresponding number on the graph here, since we are only dealing in real numbers. Going back to the graph we had before with the x and y variables switched again, we see that there is a lowest point here. The lowest point here is the lowest point of y in the equation y equals x e to the x. So, if we can find this point here, that means we can switch around the coordinates to get this point here. So, let's look at what it means to find this lowest point. Recall that to find the lowest point of a function, you must find the derivative of that function and set it equal to 0. So, we are meant to find y prime, which is the derivative of y, and set it equal to 0. Using calculus to find the derivative of x multiplied by e to the x gives the derivative of x multiplied by e to the x plus x multiplied by the derivative of e to the x. Knowing the derivative of x is 1 and the derivative of e to the x is itself, one can simplify this. Then you can factor out the e to the x term. Recall that to find the lowest point, we need to set the derivative equal to 0. For e to the x multiplied by 1 plus x to equal 0, either e to the x must be 0 or 1 plus x must be 0. E to the x can never be 0, so we know that 1 plus x must be 0. Solving for this, we get that x is just equal to negative 1. Substituting this value of x in for our equation y equals x e to the x gives negative 1 e to the negative 1, which is just negative 1 over e. So, knowing both our x and y, we can write this as a coordinate point. And now we have our low point at negative 1 over e. Now we can switch around the x and y variables, which means switching around the x and y coordinates to get this point. This leads us to say that, according to this graph, the product logarithm of negative 1 over e is going to be negative 1. Except, of course, this only works as a general statement when looking at the graph. There is something incomplete about this, and it's that we haven't specified which branch of the product logarithm we are meant to be using. So, allow me to go over what these branches are. Zooming in a bit on the graph of the product logarithm, we can notice that for some negative numbers, we see the product logarithm of x having what appears to be two corresponding y coordinates. Here's an example where we see what appears to be two y values for a given x value. Well, as it turns out, this graph can be split into two branches of the product logarithm. The orange branch here is branch 0, and the blue branch here is branch negative 1. Another name for branch 0 is the principal branch. So the orange line here would be the principal branch of the product logarithm. If you are wondering what the other branches are, branch 1, 2, or negative 2, for example, they are values on the complex number plane that use imaginary numbers to find a solution to the problem x equals y e to the y. When it comes to real numbers, though, only branches 0 and negative 1 are used, so those are what I'll focus on for this video. So going back to our particular value here, you could correctly say that the product logarithm of negative 1 over e at the principal branch is negative 1. So we've looked at this particular value. Now let's look at other particular values of the principal branch. The product logarithm of 0 at the principal branch is just going to be 0, which you can see on the graph. It is also easy to prove this using the definition of the product logarithm. Another particular value is that the product logarithm of e at the principal branch is just going to be 1, which is also easy to prove using the definition of the product logarithm. An interesting particular value of the product logarithm is the principal branch at 1. This gives what is called the omega constant. This constant is approximately equal to 0.56714. These are some interesting values on the principal branch, definitely, but what about the negative first branch? Well, let's look at the principal branch at the point negative natural log 2 over 2. One finds this to be equal to negative natural log 2. This can be easily proven using the definition of the product logarithm. But if you look at the point negative natural log 2 for x, you see two corresponding points, and of course the other point is the negative first branch. As it turns out, in the negative first branch, the product logarithm of negative natural log 2 over 2 is equal to negative 2 natural log 2. This can also be shown using the definition of the product logarithm, but I'll leave that for you to do if you want a fun and random math exercise. Plug in negative 2 natural log 2 for x in the equation x e to the x and see if you get negative natural log 2 over 2 like you're meant to. Now that I've gone over particular values of the product logarithm function, I will now go into the calculus properties behind it. Using the definition of the product logarithm function here, I will now proceed to find the derivative. What I'll do is I'll take the derivative of both sides of the equation. Using calculus to expand this, I get the derivative of the product logarithm multiplied by e to the product logarithm plus the product logarithm multiplied by the derivative of e to the product logarithm, which is equal to the derivative of x, which is quite the mouthful. From now on, I'll just say wx instead of the product logarithm for simplicity. Also, I'll assume for the rest of this video that you are familiar with calculus, as I will be using calculus to prove both the derivative and indefinite integral of w of x. We'll write the derivative of w of x as w prime x, which is what we're solving for. On the right side, we know that the derivative of x is just 1, so we can rewrite it all like this. Now we can rewrite the derivative of e to the wx as e to the wx multiplied by w prime x. Now factor the w prime x out. Notice that by the definition of the product logarithm, this expression here would just be x. So we can substitute x and divide both sides by e to the wx plus x. Then you can multiply both the numerator and denominator by wx. And then notice that, once again, this is just x, which gives you your final answer, that the derivative of the product logarithm is wx over x plus xwx. Next, I will find the indefinite integral of w of x. The method for doing this is quite interesting and creative. What I'll do is I'll put what we've already proven to be the derivative of w of x in the top right to aid us in finding the indefinite integral. Our first step is using integration by parts. We'll call our u equal to w of x and our dv equal to dx. Using the derivative of w of x in the top corner, we now have our du. Finding the integral of dx, we know that our v is just going to be x. This is a formula for integration by parts. Using our values for u, du, dv, and v, we can plug all these into the formula for integration by parts to evaluate the integral. And we know that u dv is just going to be wx dx. So expanding the integral using integration by parts gives wx times x minus the integral of wx over x plus xwx all times x dx. So what we need to do now is evaluate this integral. You may notice that we could multiply x into the fraction and simplify, but I am not going to do that because one finds it easier to find this integral if I keep it like this for now. What we're going to do is use our u and du from earlier again, this time not for integration by parts though, noticing that our du is already in the integral. Recall the definition of the product logarithm. Since we are using u, which is said to be equal to w of x, we can substitute u into the definition. We get that u e to the u is equal to x, and x is in our integral. And remembering that the rest of our integral is just du, we can rewrite this whole integral as the integral of u e to the u du. What we need to do now is to use integration by parts again, and to do this, I'll introduce terms u1 and dv1, calling u1 equal to u and dv1 equal to e to the u du. We can then see that du1 is just going to be du, and v1 is just going to be e to the u. Using integration by parts again, we see that our integral is equal to u1 multiplied by v1, which is just u e to the u, minus the integral of v1 multiplied by du1, which is the integral of e to the u du, which is just going to be itself. Now that we've found this integral, we can substitute it back into what we had before. Recall that we've already showed that u e to the u is just x, so we can rewrite this as x minus e to the u. Rewriting u e to the u equals x by dividing both sides by u gives that e to the u is equal to x over u. Substituting this for e to the u gives x minus x over u. And recall that u is just wx. So we can substitute that in here. Now that we have found this integral, we can substitute it back into the integral we were trying to find before. And then we can expand subtraction to the terms, then rearrange the terms, getting us our final answer, not forgetting to add plus c at the end. And so, we have now proven the indefinite integral of the product logarithm. And that brings us to the end of this video. If you found this interesting, please leave a like and subscribe, and feel free to check out my other videos. Leave a comment on what you thought about this video or about videos you'd like to see in the future. Farewell for now.